I decided to just revisit our open and closed and boundary sets, interior and boundary points discussion, which we stopped at on Friday, quickly. So that's where we were. I need this Jonathan Kress file, I'm sorry. That's the one. That's a definition we discussed with you on Friday. Two types of points we introduced in relation to a domain. Interior point is the one which comes in, which belongs to the domain together with some ball around that, or disk. If it is on a plane, then it's a disk. Otherwise, as we call it a ball, you can call it a ball in any time. Boundary point is the one which, no matter how small you make your ball around that point, there will be both points from the domain and from the outside the domain. If this is the case, in that case, we call the point boundary. Now we have these two extra definitions. The set is called open if every point is interior. The set is closed. The set is called closed if it's complement to the open one. There's a short theorem which says set is closed if and only if it contains all of its boundary points. That's the one just to remember. We're not going to discuss detail. We're not going to discuss the proof of that. On this slide, we have very simple examples of open and closed sets, like on real line, interval together with the endpoints. That's the one which is closed. Interval without the endpoints. That's the one which is open. You can, it's relatively straightforward from the definition. Every point on the interval AB without the endpoints, it belongs to that interval together with some smaller interval which comes into AB entirely. And this property only fails for the endpoints, which are the boundaries, because for the endpoints, no matter how small you take the interval around the endpoints, there will be both points from the interval and from the outside of the interval. If it's left endpoint, from the left will be from the outside, from the right will be from the inside. Some other examples as well. So it's a closed, open, R. Open and closed, because the set R satisfies both the definition of open and the closed set. So that's why we, depending on what you need, you can call it open or you can call it closed, and that both of these statements will be true. The same true is about the empty set. It's both open and closed. For instance, it is open. For the set to be open, by definition, every point must be interior point. For the empty set, it is true every point of the empty set is interior point, because it doesn't have any set, it doesn't have any points. It's sort of the convention we always use in mathematics. Empty set possesses every properties we would like it to possess. Half open interval is neither, because the endpoint kills that. Set of rational numbers is neither. Set of the reciprocals to the integers, positive integers, is neither. Well, it is not. It's obviously not open, because for this set to be open, you need every point to be interior point. Every point must belong to the set together with the neighborhood around it, which is not true. Pick up any point from this set, and any point nearby will not be part of this set. It is not closed. You can do it by a theorem on the previous slide, because for the set to be closed, it must contain all of the boundary points. For this set, what's the boundary of this set? The boundary of this set, every point of the set itself, because every point of, take any point from this set, say 1/2. It's a typical element. It is a boundary point, because no matter how small you take the neighborhood, centered, no matter how small you take the disk or ball, or in this case it will be just an interval, it's a one-dimensional ball. No matter how small you take the ball around the point 1/2, there will always be points from the set and not from the set. The point from the set will be 1/2 itself. The point not from the set, will be just the one nearby, just very close to it. But it's not all. There's another point which is in the boundary. The point 0 is also in the boundary of the set. Because again, no matter how small you take the neighborhood around the point 0, there will always be points from the set, because the set converging to 0, reciprocals. And there will be points not from the set, take any negatives, for instance. That's why 0 is also part of the boundary. That's why this set is neither. For this set to be closed, it must also have the 0 point, the boundary point. All right. You probably will discuss this in more details in the tutorial next week. Now this time there will be examples on open and closed set. There's one example of in the n-dimensional setting. That's the example of a ball itself. If you take a ball at any point x0 with radius, any radius, epsilon, this set will be open. And I think these slides, they have the argument showing that. Let's just look into that. Here's the argument. So if you take a ball, bx0 epsilon, that's the definition of this ball. The claim is this is an open set. That's what we do. Look at this. We have to, in order to justify that claim, we have to show that every point in this ball is interior point. So every point in this ball belongs to this ball together with some other ball around it. Visually, it seems like a clear thing. Formally, that's how you do it. There will be some important piece which you have to mention all the time if you do something like this. You can say it in different ways, but there is one ingredient which must be present. Otherwise, the solution is not complete. And here it is. So for each x in my ball, that's a randomly chosen point x, we need to show that there is another ball of some other radius, delta, that's the symbol for this radius, such that this ball belongs to this blue ball, the original one, in its entirety. This symbol says subset. So look what we do. The content of the presentation is presenting this choice of a ball, or in this particular case, presenting of a choice of a radius of that ball, delta. And that's what we suggest for the radius. If you take delta, epsilon take r, where epsilon was the radius of the original ball, and r, look what the r is. R is a distance from my x0 to x. If you take such delta, then I have to convince you that this delta works. I mean, when I say works, it ensures this claim. So here's my justification for that. To show this claim, I need to convince you that every point from this delta ball will be also the point of the epsilon ball. So I take this every point. I just give a name to this every point, x dash. I need to show this implication. We still need to present some content, some justification for this implication. Look what we say. In order to convince you that this x dash in this ball, I have to measure the distance from x dash to x0. So here we are. I'm measuring this distance. And what I say is this. I can control this distance by the sum of these two distances. Why can I do that? Why can I put this inequality on my slide? Well, actually, it's Jonathan correct. Thank you very much. It's a triangle inequality. That's the combination of words which must be present in your presentation. That's the ingredient which makes things work here. By triangle inequality, I can estimate this distance by a combination of these two distances, from x0 to x and from x to x dash. Each of them individually, we have some control for them. For instance, from x0 to x, it's the r distance. Here it is. From x to x dash, that's the delta distance. Yeah, because x dash comes from this ball. Now, if you just replace what the delta was chosen for, you end up with the epsilon. So I just convince you now, with the help of triangle inequality, that this distance is controlled by epsilon. And that's the end of the proof. Yes?
What we write proofs, do we need to write the reasons for each and every step of our argument?
I think this question comes up every time in different guises. And I think in this class it also came up. Certainly, you don't have to do every step because it will be too long and unnecessary. On the other hand, choosing which step to explain which not, it is a skill which you have to learn. It depends on the actual statement you're proving. For this statement, triangle inequality is essential, important point which must be mentioned. Some other things may be skipped probably because they're not so important for the presentation. Okay? So no, you don't have to do every step. If you do every step, nobody going to read that. Like the person next to you, if you ask him to check it, he just look at it and says, no, thank you. It's too much to read. Yeah, it's not good. You have to, it's a part of the skill of writing a nice, readable, convincing proof. The skill is being able to identify the important steps and explain them. The rest may go unexplained. For this proof, the important step, how we choose delta, and the ingredient which makes it work. Triangle inequality. Yeah, that's the end of it. Okay. Well, in the same set of slides, we have a few extra definitions, like limiting point or accumulation point. That's the point which can be given as a limit of other points in a set, but not the point itself. That's a diagram which demonstrates that. It's just a definition. And some straightforward claims about this definition. Every interior point is a limit point. Why is that? Well, because the interior point comes with a ball. Within this ball, there are plenty of points which approximate your x. That's why it is the part 1. X naught is not necessarily in D. So limit point may not be in the D itself. This example of reciprocals of the positive integers, the 0 point is a limit point for that set because you can approximate that point by reciprocals of the positive integers, but the point itself is not in a set. That's the example. The set is closed if and only if it contains all of the limit points. It is another relatively simple statement. You can use this without a proof. Yeah, well, it's another definition. Interior of set D, it's a collection of all interior points. Boundary of set D, collection of all boundary points. Sometimes we use this notation for the boundary points. See, like a partial derivative D. Closure, that's relatively interesting term. Closure of a set D, it's when you take a set and you throw in the boundary of that set. That will be the closure. And the closure is always closed. Yeah, that's some examples. Yeah, closure of the rational numbers is R. Interior of D, largest open set of G, and everything. Or a few claims here. As far as I remember, there will be some tutorial questions where you will play with this. It will give you more understanding of these things. Right. I have one example where we need to test that the set is open. You just saw one example. That's the example with the ball. That's the example on the previous slide. This example. Yeah, this example. I plan to present another example. It's the example from the tutorial set, the one from the next week. Just give me a second. I have to decide whether I should do it or not. Yeah, well, I probably will skip that. Let's just go to my main set of slides. On this one, no, actually, let's just discuss that. Why not? It is sort of instructive. It's an example from the tutorial set, and the question says, let's just open that. Right. It's again about the interior and boundary points. We need to find the interior and boundary points for this set. Yeah, and it's a direct argument. There will be another argument, which I call indirect argument, a little bit later. But first, I'd like to discuss with the direct argument, and that's the Let's just try to do that. It resembles a lot what we just did for the ball. In that proof, the main step was choosing delta and indicating this triangle inequality, which works. Here here will be some other important steps, and I'll try to emphasize them. So let's just try to do that. I'll fix a point in this set. Well, that's the claim we're proving. The claim is that this set is open. This set is open, so every point in this set is interior. So every point in this set comes together with some ball around it. And so the actual content of the presentation will be presenting the radius for such ball. So I'm choosing a point which belongs to this set, so it's subject to this condition. The components of that point subject to this condition. Yeah. And now what I will do, I will present a ball around this point of some radius, and I'll present the radius such that the whole ball will be also subject to this condition. It will be part of this set. Okay? For that, I'll introduce this auxiliary number, epsilon, which will be this number. It's a positive number, isn't it? Because of this condition, it's a positive number. So look what I'm going to do. I'm going to take another point, B. Yeah. I will take another point with components x1, x2, x1 and y1, sorry. I will make an assumption that my point is delta distance away from A. Even though I haven't chosen delta, I will choose delta a little bit later, but delta will be this distance, my point B away from A. And I'm going to analyze this first. Even before I chose the delta, I'm going to analyze this inequality a little bit, and then I present the choice for delta. Look at this. So if I analyze this, we know how we compute the Euclidean distance. That's how we compute the Euclidean distance. Yeah. From this inequality, I can say this. The difference of x and x1 just by itself is less than the whole sum, is less than the Euclidean distance. So from here I can say that we have this inequality. And similarly, I can say that we have inequality for the second difference, y and y1. All of them individually less than delta. So look at this. Yeah, let's just do this. If you don't mind, I'll consider this difference for a while, which is for now. X squared take x1 squared. I will introduce these two extra terms. Take xx1 and plus xx1. And that will let me do factorization of this type. Right? Because we have a common factor x here, and we have a common factor x1 here. Yeah. Now, this inequality, that the difference between x and x1 less than delta, it tells me that the absolute value of x1 doesn't exceed the absolute value of x plus delta. It's a triangle inequality here. It's a triangle inequality here. And so, look what I'm going to say now. If I put the absolute value around this expression, it will be the same as if I put the absolute value around here and here with the less or equal sign. It's a triangle inequality. For absolute value of x, I will keep it. For absolute value of x1, I will replace it with this piece. So if I do that, that's what I'm going to end up with. This x replaced with the absolute value of x. This difference replaced with delta from here. This x1 replaced with the right-hand side here. This one replaced with delta again. So first term here delivers this term, and this delta delivers delta squared. This follows. Yeah. If you combine these two together, that's what we end up with. All of these estimates that were given for the x component, I can do similar estimates for y components. I say similar, I'm hiding the details by these dots. Similar estimates for the y components will look like this. Now, time has come to make a choice for delta. I told you before, we take 2 points, A and B, at the distance delta, and we just postpone the choice of delta for a little while. First, we did some estimates for the difference of squares here and for the difference of squares here. Now, I will choose my delta. Look at this. It will be a big choice, but you will see why we make such a choice. Here's the choice for delta. If I choose such a delta, it's a minimum of 3 numbers, one of them like that, one of them like that, and one of them like that. The important thing about this choice of delta is that it's always positive, because every component here is positive. And it is independent of my B point. B point doesn't appear here. Components of A point, yes, they are, X and Y, but B is totally ruled out from here. Now look what I can say now. If I set such a delta, it gives me this. If I take the difference between x1 square and y1 square, I'm checking this condition now for the point B. If I check that, look what I'm going to say. I split it in 3 combinations like this. Difference of x and y, and then these 2 brackets. If you cancel things out, it will be exactly this. But I do this because for this bracket I have some control. Here it is. And for this bracket I have some control. Here it is. So I'm going to use this control now. Look at this. Less or equal, this difference, I keep it as it is. Then comes this bracket. Then comes this bracket in absolute value. If you replace a number with the absolute value, the expression becomes larger. That's why we have this inequality here. I continue. For this bracket, we have this control. And for the second bracket, we have similar control. All of them combined here. And now my choice of delta start to work. Look at this. This choice of delta now start to work because this term, because delta is a minimum of these 3 numbers, it's certainly less than this. But if you replace it in this position, if you replace your delta with this first part of my minimum, which will make the expression larger, if you replace that, absolute value of x will cancel this bracket. I mean, it will be less than 1 number. 6 and this 2, it will give me this. Look at this. First one I keep. Oh, actually, I didn't say I keep. This one is replaced by, or you'd probably, I don't know if you remember what the epsilon was. It was at the top of my slide. Here it is. Oh, I can't open it. Epsilon was here. Remember, that's how I set my epsilon. If you solve here for this bracket, this bracket will be 1 take epsilon. And now I use that. I just replace this one with 1 take epsilon. For this delta, I use the first element of my minimum. If I only use the first one, the expression becomes larger. That's why probably I should put here the less or equal. Ah, no. Yeah, less or equal. It's just not the equal sign. Less or equal. Oh, actually, I did some arithmetic here in one step. So if I replace this delta with the first component here, it will be epsilon on 3. No. It will be epsilon on 3. If I replace this delta with the second one here, it will be another epsilon on 3. If I replace this delta square with this expression for delta, it will be another epsilon on 3. So actually, it should be here 3 times by epsilon on 3. Oh, I even miscalculate a little bit. Come, it's... Well, yeah, well, everything is correct, but now I see that my choice for epsilon not really good. I should have chosen here on 12. Look at this. I should have chosen here 12. 12, and 12, almost 12. That's how I should have chosen it, because on that case, it will make it epsilon on 6 here, and then it will be epsilon on 2 here, and that's the value less than 1. And what do we see? We see that x1 squared take y1 squared less than 1. That is the condition which ensures that the point comes from the set S. Yeah, that is a condition which ensures that the point comes from the set S. Believe it or not. And the important part of this proof is choice for this delta. Any questions? It's not an easy proof. Yes? Because in order to land my point in the set S, this difference must be less than 1. With my original numbers, it was epsilon here, and 1 take epsilon plus epsilon is exactly 1. It doesn't give me strictly less than 1. So I need to lower my delta. I need to squeeze my delta a little bit further to ensure that I have strictly less than 1 condition. Actually, I'm happy I made this typo, because and I'm happy you asked this question, because it tells you what we expect from the choice of delta. We choose it in such a way that I chose a delta in such a way that if I use all of the estimates I did before, they help me to ensure less than 1 condition, the condition which lands a point in the set S. Any more questions? All right, I see a lot of concern on your face. It's a difficult proof. The good news for you, there will be examples for you to practice. Very unlikely that with this sort of proof you will need to present in the writing assignment or in the tests of some sort. It's a lengthy proof and it's a difficult proof. It requires lots of thinking and design. If you can produce something like this, you become like a high-level mathematician, trust me. The reason I put this proof in the lectures just to show you that we're gonna establish the same result in a very simple way, in half a lecture, probably. Yeah, maybe even by the end of this lecture. I just want to show you that the few materials we're going to develop in the next 5 to 10 slides, they're so powerful that this direct complex proof can be reduced to a few lines. And that's the reason I put this, I just showed this in class to show you how powerful those 5 slides which are coming, how powerful they are. Yes? Well, not probably in class, but you can come after the class. I can tell you if it's shorter one or not, okay? Any other questions? Right. Yeah, why not? Let's just now go back to my main set of slides. Continuity of the function of multiple variables, just a definition. It's quite a expectable definition. You saw this definition many times. We say that the function is continuous in the point when we have this limit relation. We know it very well. We say that the function is continuous on the entire set D if it is continuous in every point of that set. You saw this definition in different guises maybe, but you saw the similar definition many times already. It's not new. Continuity by components, it's another result which we saw in case of curves. It says that if a function given by components, it is continuous if and only if every individual component is continuous. It's another result which we saw before. I just state this for the reference to make my index, remember the index which I showed you at the beginning of the class, to make my index complete and useful. Even I said it even here, you know, if you want to try this theorem, you can follow the same lines when we did a similar proof for curves. This is a new thing. It's a thing which somehow surprisingly never, like I don't know anyone in this unit put this like in writing explicitly. Continuity of elementary functions. Elementary functions, what's the elementary function? That's a definition for you. That's a function, one of the linear function. So a function f is called elementary, function of multiple arguments, function of several arguments called elementary. If it's one of the x case, one of the linear components, cosine of the component, sine of the component, exponential function of the component, an inverse function of elementary function. So an inverse of one of these, or a power of the elementary function, or algebraic of elementary function, or superposition of elementary functions. So it's sort of inductive definition. Some basic functions, which we call elementary, and some derivatives, not derivative in like analytical, like analysis derivative, but something which is derived from like basic functions. Any function which is constructed in this way, from this 5, we call them elementary function. For instance, log function, it falls into the category inverse of elementary function. It's inverse of the exponential. Tangent function, it's elementary function because it's algebraic combination of two elementary functions, cos and sine. Sine and cos, it's algebraic combination. So effectively, every function you know, you can fit into this definition. Almost every function you know. Do you know a function? Do you know any function which you cannot fit in this definition? Yes. No, you can, of course. Hyperbolic is a combination of exponentials.
Error function.
Which one?
Error function.
Error function. How many people know in this class what the error function is? Yeah, well, that's functions built by the integrals here. Many of them non-elementary. That's true. Any other examples? Taylor series. Okay, all right. Yeah, well, I see you know some non-elementary functions. Yes. Okay, that is what elementary function is. And the good news for you, when you want to see when elementary function is continuous, I have this beautiful result for you, which you can reference without any proof. Elementary function is continuous everywhere where it is defined. As e. I'm surprised no one ever mentioned this in writing in this course. Like if you open a yellow book in the first year, does it have anything about elementary functions and when they are continuous? Do you remember from the top of your head? Aye? You think so? Can you show, if you have free time some other time, can you show me the reference? I want to have a look into that. That's a very good result, which tells us that many functions we know, almost every function we know, we can claim that they are continuous very quickly. As long as they are defined, they are continuous. So as long as we remove those points where we have division by 0, where we have the log of the negative numbers, what else? When we have what else spoils the domain of the functions? When we have roots of negative numbers, and it's another occasion where we have to exclude points from the consideration. As long as we exclude all of those points, the rest will be the set where a function is continuous, and you don't have to do much about that. Right, and now this result which I promised to you, look at this. That's a bit of a definition. A set of this type, it's called pre-image. So look at this. It's a collection of, so if you have a function which maps n-dimensional space into m-dimensional space, or subset of n-dimensional into the m-dimensional. For a set U in the codomain, you take all those points in the domain, which end up in U after you apply F to them. If you collect all of those points in the domain, you call this pre-image of a set U under the map F. That's what we call pre-image. Now the result I'd like to discuss with you is this one. The map F, or the mapping F, is continuous if and only if the pre-image of every open set is open by itself. And that's if and only if result, by the way. Pre-image is open if and only if, no, I should say the other way around. The pre-image of every open set is open if and only if the function f is continuous. On one hand, if you have a continuous function, you can always expect that the pre-image of the open set will be open, and the other way around. If you show that the pre-image of open set is always open, the map is continuous. And a similar clause about the closed sets. The pre-image of the closed set is always closed for the continuous map, and the other way around. If the pre-image of a closed set is always closed, the map is continuous. Why did I mention this theorem here? Here's the example we just did in this lengthy, really difficult way. This set we just considered with you, remember this set? We just proved it's open with you. Now we can, if I use the result on my previous slide, that the pre-image of the open set is always open for a continuous function, I can argue that this set is open in two lines. First line is that this function is continuous because it is elementary, right? It's a combination of x and y, squares difference. It's elementary function. By the theorem 2 slides ago, this function is continuous every time it is defined. And this function defined everywhere. So it is everywhere continuous. So f is continuous. On the other hand, this v set, it's the pre-image. It's the pre-image of this open set in the codomain of my map. It's exactly the pre-image. And by the theorem on the previous slide, this pre-image must be open. Everything fit on one single slide. That horrible lengthy proof where I needed to convince you that I can choose a delta explicitly and I made a typo and we fixed that, we can do it in one slide if we use two theorems. One of them, continuity of elementary functions. Second one, pre-image of the open sets in case map is continuous. So when you have these questions in the tutorial, on one hand, I expect you to be able to produce something like this. It's very quick, and you can learn how to do it. On the other hand, if you like challenges, you can try to do a direct proof for those examples. Direct proof like we did 15 minutes ago. If you can do a direct one, you can be really proud for yourself. Like I said, no stress. There won't be this direct proof in the test, even the exam. Probably, no, it won't be. No stress about that. It's a difficult proof. It requires significant skill and significant insight into the analysis. At this level of your mathematical development, we probably don't expect that yet. I mean, we don't expect that as a compulsory skill to pass this topic. But this one, this way to do it, we expect that you can do something like this because this is relatively easy, just a combination of two theorems in the right way. And doesn't require much. Any questions? You don't have any questions? How do you think? Look, I want to ask you this. When we did this result, right? When we did this, the same proof of my direct argument, which was really lengthy, now we did it with the help of two theorems about the continuity of elementary functions and this pre-image result. Given that I believe in the law of conservation of difficulties, right? Where does the difficulty went? Where did the difficulty go here? In the proof of those two theorems, you say, right? It might be so, because you see, I'm asking you this because I have the proof of one of them ready to show you, and it's not really that difficult. We have 7 minutes. I think we can look into that, can we? So it somehow disproves the law of conservation of difficulties. Maybe it doesn't. Let's have a look at the proof. Maybe I'm wrong. Maybe it's only easy for me. But actually, it fits on one page of a slide. Unlike this direct presentation, which took 2 spreads of slides, that one fits on 1 spread of a slide. So here's the result: continuity via pre-image tests, I called it. So we have a function which maps the main in Rn into Rm. Yeah, that's how we define pre-image. That's how we define pre-image. Yeah. And the theorem claims that f is continuous if and only if the pre-image of every open set is open. I'll show you probably one way. Both ways fits on this slide. Both ways, just one spread of a slide contains the complete proof for this theorem. So let's just go this way. Let's just fix an open set. So when I say we go this way, my assumptions are like this. We assume that f is continuous, the way we defined it. And we also assume that U is open set. We need to conclude that pre-image is also open set. It's very good proof, actually. I mean, because it just shows you all of the concepts in one slide. So look at this. I fix a point in my pre-image. Remember, I need to convince you that pre-image is an open set. For that, I need to convince you that every element of the pre-image comes together with the ball in the pre-image. That's for the set to be open. That's what we need to show. So I fix a point. Point being in a pre-image is the same as the image of that point being in U itself. That's the definition here. U is assumed to be open, right? Every point in the open set comes together with the ball. So since U is open, I can say that this point in my set comes together with the ball, right? There is a little ball around this point which entirely within U. That's because U is open. Now, since f is continuous, that's the point where we use the second assumption, that f is continuous. What do we know for the continuity? For the continuity, we know that for every positive epsilon, there is delta, such that, well, I can show, such that every point at delta distance from the x goes in the point at epsilon distance from the f of x. That's a definition of continuity in terms of epsilon delta definition. If I just condense this into this line, which says image of the delta ball around x goes into epsilon ball around f of x, and if I now reinterpret this in terms of the pre-image, that will be exactly this. That the ball, thank you, that the ball around x, delta radius, belongs to the pre-image of this epsilon ball, which is even smaller than the pre-image of U. And that's the end of it. Look at this. I fixed the point. I fixed the point in my set, and I presented you explicitly the choice for the radius of a ball around this point, which goes entirely within the pre-image f negative 1U. Every point within the pre-image comes together with the ball. It means that the pre-image is the open set. The ingredient here, the key ingredient here, U is open and F is continuous. And that's the end of it, the end of the forward proof. Hence, F negative 1 U is open. The opposite one, even shorter. The opposite one now says this: if this is true, if pre-image of every open set is open, F must be continuous. And I'll check it by definition, by epsilon delta definition. Look at this. I fix X point and I fix epsilon, positive one. Since the ball of radius of any ball is open set, we just prove it today with you. Ball is an open set. The pre-image of the open set is open, isn't it? It's just the assumption now we have. For every open set, the pre-image is open. That's the assumption that we're starting off. And this is an example of the open set. If I take a pre-image, this will be open. Now, I would like to interpret what it means this to be open. It means that, well, in this set, I have point x, right? Because point belongs to the pre-image when the image of this point belongs to the ball itself, and f of x belongs to that ball, the center of that ball. And because this set is open, this x belongs to this set together with some ball around it. And that means there is a radius, delta, such that x belongs to this set together with the ball. Actually, I lied to you a little bit. It doesn't fit on the entire slide. I have to scroll it up a little bit. Yeah. Well, it's just, all I have to do, I have to say that this embedding, it is here already. If I just reinterpret this embedding like this, thank you very much. If I reinterpret this embedding like this, it will be exactly the definition of continuity, right? Because look at this. That is, f, this ball is taken entirely into this ball. Look at this. For every positive epsilon, I found delta. Here it is, explicit choice for delta, such that the ball around x goes into the epsilon ball around f of x. This is a definition of continuity, and that's the finish of the proof. So you were right, actually, a little bit. This is not as difficult as my direct argument, but still, it just takes a little bit of that difficulty inside. But after we have this theorem, those questions in the tutorial, and you will have quite a few, you can do them in a really simple way via these two theorems, one about the elementary functions and the other about the pre-images in case f is continuous. So it's a really two powerful tools, and you have to learn how to use them together. Any questions? No? All right, thank you very much for your patience. It was a really difficult proofs. I'll see you all the day after tomorrow.